We have explored the vast potential and diverse technologies of geothermal energy. Now, as we begin to look into its real-world context, we must address the critical question. What is the environmental impact of harnessing this planetary heat? To address this, we'll conduct a scientific analysis of geothermal's footprint, focusing on three key areas: life cycle emissions, land use, and water consumption. When assessing emissions, we must consider the entire life cycle. Geothermal's primary advantage is its extremely low operational emissions. Unlike fossil fuels, nothing is burned to generate heat. Modern binary cycle plants, which are closed-loop systems, can operate with virtually zero emissions. However, older open-loop flash steam plants can release naturally occurring non-condensable gases that are dissolved in the geothermal fluid. These can include carbon dioxide and hydrogen sulfide. While the carbon dioxide levels are significantly lower than fossil fuel plants, hydrogen sulfide requires management due to its rotten egg smell and toxicity at high concentrations. Modern systems often capture and re-inject these gases or use abatement technologies. Finally, like any large infrastructure project, there are embodied emissions from the manufacturing of steel and cement used during construction. A key environmental advantage of geothermal energy is its high power density. This refers to the amount of energy that can be generated per unit of land area. Geothermal power plants have one of the smallest physical footprints of any utility scale power source. The majority of the system is deep underground, and the facilities, the power plant, pipes, and cooling towers are relatively compact. While the exploration and drilling phases cause temporary land disturbance, the long-term operational footprint is minimal compared to the vast arrays required for solar or the wide spacing needed for wind turbines to produce an equivalent amount of continuous energy. Water use in geothermal plants is highly dependent on the plant's technology and cooling method. Older open-loop flash plants can be water intensive as they use evaporative cooling towers to condense the steam back into water. However, modern closed-loop binary plants inherently conserve the geothermal fluid. Furthermore, many new plants are designed with air cooling systems which use fans to cool the working fluid, reducing water consumption by over 90% and making them suitable for arid regions. A critical aspect of any geothermal project is groundwater protection. Wells are constructed with multiple layers of steel casing and cement to isolate the geothermal fluids and prevent any contamination of shallow freshwater aquifers. Two other impacts are often discussed: induced seismicity and noise. The hydraulic stimulation used in enhanced geothermal systems can induce very small seismic events, typically too small to be felt. These are carefully monitored to ensure that they remain within safe, non-damaging limits. Noise is also a factor, but it is primarily confined to the construction and drilling phases. During operation, modern geothermal plants are relatively quiet. These impacts are well understood and managed through careful site selection and engineering controls. In summary, while no energy source has zero impact, geothermal energy presents a strong environmental profile characterized by low cycle emissions and a minimal land footprint. The key challenges, such as water use and induced seismicity, are being effectively addressed by modern technology and best practices. In our next video, we will examine the other side of the coin, the economic viability of geothermal projects.